So just to kind of get um, you guys going a little bit before we um, start in a minute. Um, if you go on our Canvas page, so we're going to try to make this as much like the normal um, lab discussions that we were having, where I give you guys some problems, you work on them, and then we talk about them before the quiz. Um, So in this section on Canvas, this module called Lab Notes, if you click on this, this has the problems um, that I'd like you guys to work on. So it has um, questions involving limits. The last two are just the very beginning of talking about series. The rest is about sequences. Um, so you can try these out. What there also is on that page um, are these solutions. This is here partly so you can use it um, after this session to go over these problems, but also since I'm going to be making some breakout rooms, so splitting you guys up into smaller groups, and then I can pop into those and ask questions, but that's not always the most convenient. So if you are stumped and I'm not in your room to help answer questions, you can look at these solutions. I would really recommend trying the problems on your own. Like um, it's always been these first problems aren't going to be graded. They're not turned in or anything. So it's just a place for you to practice, see how much understanding you have, where you're missing. And these solutions are there to help you get really unstuck. Or if you think you've got it, you can go check your answer. And if there's any confusion about why your answer isn't what the solution says, then when I pop in, you can ask me about that. Um, so, right. So find these on Canvas, and then I'll split you guys up into some breakout rooms, and you guys can get started. And like before, if you want to try them on your own, go for it. But if you want to turn on your mics and videos and talk about the problems, um, that would, I think, help everyone kind of figure out uh, how these problems go and where they need some help. So let me split. Do these. Let's see. So let's do that and okay. So join those rooms. I'll be popping in kind of between them, but okay. So join those rooms, and I'll be coming in to check on how you guys are doing. And Jade, so before you join your room, on Canvas in the lab notes module, there are these problems. Those are the ones we'll be starting with. The solutions are there, so you kind of check as you go. If you're really stuck and don't want to wait for me to hop in, you can take a look at that. But for the first chunk, try these problems out. And the breakout room will be a smaller group so you can talk to some other students to figure out how these problems go. Let's read the recording. Okay, so hopefully that went all right. It's a weird situation, but I think this software works moderately well at recreating um, some of the discussion lab experience. So let's talk about these problems. And just to put it out there, what's going to happen, the quiz, you'll have a while to work on it, like something like an hour. It won't take nearly that long, but just to make sure that you have some time to get whatever materials you need and take the quiz and then upload it through everything. Also, the last two problems on here are talking about series, and there won't be series problems on the quiz. We'll still talk about them here, just because it's good to get more familiar with them, but we'll focus on the sequence things. So the first part is, here are a bunch of sequences. How do we find the limit? And what's going on in these is it's not that helpful to, at least right away, think of them as like analogs of a function of a variable x. It's really some sequence specific stuff going on. So you can, I guess, follow me. These solutions are also on Canvas, so you can look at them. For really the first two, the strategy is the same. First, take the limit of the sequence without the -1 to the n. So the -1 to the n is alternating between 1 and -1. Forget about that for a second and just take the limit of 1 over natural log of n, so replace the top with a 1, and the limit of 3n over n minus 4, so forget about that factor. And these limits without the alternating part are easier to deal with. In the first one, the natural log goes to infinity, so the fraction goes to 0. In the second one, you can either use L'Hopital's rule or notice that the degrees match. There's an n on the top and bottom. And since those match, you form the fraction out of the 3 here and the 1 that we don't write there, and that's where the limit 3 comes from. Then we have this kind of fact or pair of facts about what happens with alternating sequences. And what really happens is, if you take a sequence whose limit is 0 and you make it alternating, that limit of the alternating sequence is also going to be 0. So what this looks like, a quick picture, is 1 over n is going to 0, so it's positive the whole time and going down towards the x-axis. If you put the alternating part on, what's happening is you're positive and then negative, you're positive and then negative. So it is still alternating because of that -1 to the n, but the bounces on either side get smaller and smaller. So what's happening is you're still positive and negative on alternating terms, but you are still getting closer to 0. So that's graphically what is happening. And in general, this is the situation. If you have a sequence that goes to 0, the alternating version of that sequence also goes to 0. In the second case, we have something different happening. If we have 3 and -3, what we know is the non-alternating version without the -1 to the n, that's going to 3. But what happens if you put that minus sign on is, when this is a positive one, you have terms that are heading up towards that are heading up towards 3, but when it's negative, it makes the terms go down towards -3. So the top part is going up towards 3, the bottom part is going down towards -3, and so then the sequence as a whole is bouncing between things up here and things down here, so it's not settling in on one single value. Okay. And so the breakdown is really, it's alternating in both cases. Look at the non-alternating version. If it goes to 0, the alternating version goes to 0. If the non-alternating version goes to anything other than 0, then the alternating version that we're really interested in, that limit doesn't exist or the sequence diverges. Questions about those two, which kind of come as a set. Okay. So let's get rid of all my little dots. So for part C, there's not a lot of work, but you need to know what to do with these numbers here. And what's happening is we have these limit laws that say, essentially, if you have a sequence with a lot of different parts, take the limit of each part, and once you've taken those limits, you end up with a number, and then see what number you actually get. So in particular, we're taking a limit of this whole thing. We can take the limit of the two pieces individually and then subtract what we get. Over here, we can take the limit of the top and bottom separately. So when we take the limit of the bottom, that's the limit of Cn, we know what that's doing. We know that's going to 2. On the top, we're taking the limit of 3 times Bn, and how we can do that is take the limit of Bn, whatever that number is, multiply it by the 3 that's here. And Bn, that has a limit of 6, so the top is 3 times 6, or 18. And in the second part, we can also say the limit of 4 times the square root of An. Well, let's take the limit of the square root part, multiply that by 4, and also we can say take the limit of the inside, An, and whatever that is, take the square root of it. So that's where this Bn is going to 6, so that's the number that shows up there. Cn is going to 2, that's where that shows up. The An inside the square root is going to 4, and so we get this number and then simplify. 18 over 2 is 9, 4 times 2 is 8. We're subtracting, so we get +1. Questions about that part? Okay. In the last part of this problem, with these factorials are difficult to deal with, so the most common way of handling them is write them as a lot of things multiplied out. So n factorial says start at 1 and then multiply all the numbers up until you get to n. We do the same thing with n minus 1. Start 1, 2, 3, and so on up until n minus 1. But on the top n factorial, n minus 1 is the factor right before it. So we have an n minus 1 here, and then the last thing we multiply on is n. But then if we write this out, what we're seeing is if you were to pick a specific n and write this out, so 4 factorial is 1 times 2 times 3 times 4, 4 minus 1 factorial is 1 times 2 times 3. You get a lot of cancellation, and the only thing that's left is the extra factor of n that's on the top. So writing these out as a product, the 1s, the 2s, the 3s, and the n minus 1s cancel. So what this expression really is it's just n. And this is something we can take the limit of. This limit goes to infinity, and the sequence diverges. So with factorials, the way we really understand them is writing them out as a product. Okay. For the second question here, this is one day where we're talking about things like bounded and monotone and the monotone convergence theorem, which says if you know your sequence is monotone and bounded, then it's going to converge. And knowing that it has a limit helps us actually find the limit. So the first part is just how do you compute these? And the real process is you're given some starting number, put that 4 into this formula, and that tells you the next number. So A1 is what we start with. If we put this 4 in here, 5 over 6 minus 4 is 5/2, and that's the second term of the sequence. Now keep feeding that 5/2 into this formula, and that'll tell you what the next number is. So if you put 5/2 in here, 6 is 12/2 minus 5/2 is 7/2. And if you simplify this fraction, you get 10/7. To find the next term, take 10/7, and that's what goes in here. That's 42/7 minus 10/7 is 32/7. Flipping and multiplying, we get 35/32. And if we want the next term, we'd put 35 over 32 in here, simplify that fraction, and see what we get. So that's how these recursive sequences work. You have one term, put it in the formula to find the next term. Then what you get, put that in the formula to find the next term. So you can find any term that you want, just the issue is you have to find all the terms before it. You can't just, like these ones, say, this sequence n factorial over n minus 1, this is a formula, put in 10, simplify, and that tells you what the 10th term is. If we want the 10th term here, we have to find the 9th term, and for that we need the 8th, and for that the 7th, the 6th, and the 5th, all the way down. So B is really just saying, look at these numbers and notice that they are getting smaller. It's easier to tell if you have the decimals, but these numbers are 3 apart and the denominators are getting bigger, so they are getting smaller. And they're also all bounded below by 1. Each of these numbers is bigger than 1, and they're getting closer to 1. So what this part is, there's not really work, just kind of notice that the properties that we're saying keep happening, we do actually see them in these first few terms. Given that the sequence keeps decreasing and is bounded below, we can find the limit of the sequence. One thing is that we know the limit exists because it's decreasing and bounded below. So it keeps going down, but can keep going down like to negative infinity, so it must be leveling off somewhere. How this works is that we know that a sequence converges, so call its limit L. The limit of an plus 1, what this is saying is an looks like 4, 5/2, 10/7, 34, 32, and so on. An plus 1 is saying start one term later. So the first term of this is 5/2, the second term is 10/7. So you get the same list of numbers, just an has an extra term at the beginning. And if it's the same list of numbers, the limit is the same as it is for an. How this is helpful is that you look at this expression right here, and you take the limit of this. And what happens is that the limit of the left side is L. And when you take the limit of the right side, you can break the limit up over the fraction, split it up over subtraction, and you're really just seeing what's the limit of an. And that was also this number that we called L. And so what we get is written down here. We have an equation involving L, and L is the number we want to find. We want to know what the limit is. We called that L. So now we have an equation and we can solve this for L. So solving this, we can walk through it quickly, clear the denominators, factor this out, and then and rearrange things to get L squared minus 6L plus 5 equals 0. This factors, or this polynomial factors to be L minus 1 and L minus 5. So we get two solutions, 1 and 5. But limits only have one answer. So we need to pick which of these is the right answer. The way that we decide this is we look and see what do we know about our sequence. We started at 4 and we're decreasing. And if we start at 4 and we're going down, there's no way our limit is 5 because we'd have to go up to get there. So if we start at 4 and decreasing, and these are our options, we have to be going towards L equals 1. Questions about this problem? Okay. So let's squeeze these last ones in here. I guess there's not a lot of work that we have to show at least. So 3 is talking about geometric sequences and geometric series. So for sequences, so what happens to this list of numbers as you take bigger and bigger n? In this case, geometric sequences, if your R, the common ratio is a word for it, the thing being raised to the nth power, if this is between 1 and -1, the limit is 0. So in this case, there isn't really work to do. It's just saying my R is between 1 and -1, so the limit is 0, and that's how geometric sequences work. For series, we can really similarly say we know how they work. We just have to notice that in this case, the A is 2 here, the R is 3/5, and the formula when we start at 0 is A over 1 minus R. So from the way the geometric sequence is given, we can say R is between 1 and -1, so we know it converges, and we know what it converges to. And then we simplify this fraction, 2 over 2/5, and that simplifies to be 5. And to really quickly explain this last problem, what's happening here is there's some sequence an, and we know, or we want to know what the series converges to. And so how we've defined what a series means is, let me draw this, that we're looking at these things Sn. What Sn stands for is take the terms of our sequence an and add up all the terms up to an. So S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3. And we see what happens as we add more and more of these terms together. What's happening in this case is we want to know the limit of this sequence of partial sums, and we're told that if you take all these terms and add them up, no matter what n you stop with, this is a formula for what you get. So we don't actually know what the a's are, but we do know what happens if you add a bunch of them up. So in this case, what really is the work, or what you need to know is you need to recognize, to find this sequence or to find this series, I take the limit of the nth partial sums, and I'm told exactly a formula for what those sums are. So the work here is take the limit of this expression, and in here the powers are both 2, so use the 2 and 4 to form the fraction, the 2 and 4 being their coefficients, and 2 divided by 4 is 1/2. So in this case, you're really given the thing you need to take the limit of. The problem is knowing, if this is the quantity I want to find, what does that mean? And this says, take more and more of these a's and add them up and see what happens to that sequence of sums. And we're given what those sums add up to be for every n where you stop. And so that's what we take the limit of. Okay. Sorry for keeping you a few minutes over. I can stick around if you have any questions, but look for an assignment showing up soon, which is a quiz. It looks like the quizzes we've taken. You don't have to write on the quiz form, just on your own paper, and then submit that in the assignment on Canvas. You'll have a while to do it, like an hour. It won't take that long, but just to make sure that you have time to overcome any technical issues. Right. So I can stick around if you have any questions. If not, then you guys can head out and watch for that assignment, that quiz, to show up in the next few minutes. If it isn't there soon, send me an email and we'll see what the issue is. Yeah, so if you don't have any questions, hopefully this lab recreated enough of the typical lab experience that it was helpful. Yeah, and I'll see you guys tomorrow.